Hi, everyone. Thanks for joining us for another professional development seminar. Today's talk is on fire protection and life safety. Our speakers are from Kaufman Engineers. It's my honor to introduce Mr. Richard Harvey and Mr. Eliot Jordan. Mr. Harvey has over 30 years of professional engineering and project management experience on fire protection and life safety systems in Alaska. Mr. Jordan has 19 years of professional design experience of commercial and institutional HVAC, fire suppression, fire alarm, and life safety code analysis projects from diverse array of sectors. Thanks for being here, and we are very excited for your talk.
Thank you. Good morning, everybody. Today's topic, as we mentioned, is Introduction to Fire Protection Engineering, because life safety is kind of a big deal. We've got an agenda today we're trying to go through. We've done the introductions. We'll provide a brief overview of what fire protection engineering is about, discuss the roles and responsibilities as a fire protection engineer. We'll talk a little bit about active fire protection, passive fire protection, do a little bit of discussion on fire hazard evaluations and analysis, talk about egress analysis, emergency response principles, performance-based approach, and we'll also throw in some wildfire discussions. Introductions for myself and for Eliot. So I'll turn it over to Eliot.
So, fire protection engineering, I guess, kind of break this down to the understanding of what it is that we're talking. You know, at its base, we're looking at fire science. We're looking at the discussion of fire systems, fires as it relates to a chemical reaction related to heat, fuel, and oxygen, and basically having an uncontrolled reaction. The four components typically represented, you know, the oxygen, the heat, the fuel, and then that uncontrolled reaction within the middle. We are, you know, we are here to react to the fire and the life safety components related to the fire. What is a fire protection engineer? We look at the Society of Fire Protection Engineers defines a fire protection engineer, an individual who by formal training, professional experience, carries the necessary competency and the skills to provide guidance and direction to protect life, property, environment from the threats posed by fire and its related mechanism. Just to get to the formal definition, there it is. But the reality is life safety is kind of the important key here. We're always looking at the probability of one for a fire scenario. So our job is to then look at what are those ramifications, what type of protections need to be in place, what is the design of a facility, what is the design of a process that allows us to react to a fire event. So one thing to look at is, you know, the standard view of what it is that a fire protection engineer does is you look at the red boxes, red pipe. That kind of seems to be the standard definition that I get off of people when we get conversations about what it is I do. However, building construction type, facility siting, structural fire protection, egress analysis, specialty code study, code variants when you need to step outside of just prescriptive codes, smoke management, fire dynamic and modeling. We can do this as a part of a prescriptive design where we take the codes and we follow along and we follow each of the prescriptive requirements, or we can look at performance-based design compliance where we actually try to prove equivalence or betterment above and beyond the code.
Okay, we'll talk a little bit about emergency response actions, which is a component of fire protection engineering. Some of the key components for response and preparedness, detection of the emergency, notification to the occupants and the emergency response offices of the emergency. We need to ensure the occupants react to the emergency and they react promptly and in the proper format, which involves the evacuation of the occupants, which is the most important aspect of life safety within the fire protection engineering. And we also need to look at the emergency response and how the emergency responders will assist in controlling, extinguishing the fire, and evacuating the personnel that might not be able to evacuate on their own. There's a very interesting YouTube. You could look that link up because we're trying to avoid this. This is an accident that happened in a refinery in Wisconsin in April 2017. There was an incident within this refinery, very remote from this tank location. The fire escalated and cascaded, caused a pressure vessel to rupture, and the pressure vessel actually punctured the side of this tank. There's the dike, and you can see that there's a problem. There was a huge loss. Fortunately, nobody lost their life in this event, but it did significant damage to the plant, as you can see here. This is after the fact, after they finally got the fire extinguished. It took them 2 or 3 days to let this fire burn out because they lost their capabilities of fighting the fire, and they didn't have the resources. So they basically ended up having to sit back and watch it burn and make sure it didn't spread beyond the refinery. It was asphalt, bitumen asphalt material. But you can see other tanks were also damaged. I don't know for sure what was in the other tanks, but this is part of what we're trying to avoid as fire protection engineers. So the state of Alaska has recently, within the last 7 years, has established a separate discipline for fire protection engineering. And they have a license within the state now. A lot of the other states have had them already. Alaska was a little bit behind the 8 ball with most of the states. Prior to 2003, the state of Alaska allowed fire protection systems to be designed by licensed mechanical or electrical engineers with the relevant fire protection engineering experience. In 2013, the state board adopted fire protection as a separate discipline. The current state statutes that are implemented are very similar to what was previous in 2013, but they now also recognize registered fire protection engineers as well are capable of performing fire protection engineering. The state of Alaska also has a fire permit holder program for designing and installing and maintaining fire protection systems. In order to achieve your permit within the state, you have to pass a NICET Level 3 certification. NICET has 3 programs. The state has adopted those 3 programs. One of the programs is the fire alarm system, and the NICET certification encompasses all 3 of these sectors. You have a water-based fire protection systems, and you also have special hazard systems. Okay, sorry. So we'll let Eliot take over.
So, an overview of fire protection engineering. So we've touched on fire, our red boxes and our red pipe systems. We'll take a look at fire protection engineering. So the inclusion of the engineering portion of this is to look at fire sciences, actually evaluating flame spread, smoke development, fire dynamics, the actual physical processes of the fire. The codes and regulations, so the actual compliance with those codes, and take into account the regulations within design of new systems or remodels of older systems. And by systems, I'm talking facilities, I'm talking individual components within those facilities, we're talking processes, whatnot. That's the big picture component that we're trying to look at. So you have active fire protection systems, so that's going to be your sprinklers, your alarms, anything that has something that's going to move or make noise. You got your passive fire protection, and it's also very important. So it's your compartmentation of your spaces, so you keep a fire contained to a location. That's your separations of major areas of buildings, your firewalls, your fire dampers, those things that maintain and keep your smoke and your fire from spreading from point A to point B, and allows your occupants to remain safe. The occupants are the most important component in this. We can look at occupant safety being very important in this. We can also look at protection of assets within a building, but first and foremost, occupant safety takes precedence. Emergency response and management, so that's helping and creating the tools for those that are the first responders to come in and actually attack a fire after it's been created. So we also have to take into account within the design those components that are there for the first responders. Escape facilities, so we got the emergency exits, fire lifts, etc. Building design, layout, and space planning. A lot of times with fire protection engineering, you're working hand in hand with architects and those laying out the facilities so that you are actually doing something within compliance within the code and allowing safety of occupants to be accounted for. And fire prevention programs, fire dynamics computational fire modeling, where we actually get into modeling of fires to prove equivalencies, to prove system functioning, to do verification of things like smoke control, that you're actually getting a functioning system. Human behavior during fire events, something of relative high importance would be, and we'll touch on this a little bit later in the presentation, but how does a human react to a fire event? You know, we're not all still in elementary school where we had a very rote response to a fire alarm going off. Fire hazard and risk analysis, including economic factors, and then wildfire management. Not comprehensive, but certainly covers a lot of the components that fire protection engineering involves. The roles and responsibilities of a fire protection engineer: identification of hazards within your facility, within your process, characterization of that risk, of each of those risks within the facility you're working on and designing. Design safeguards that aid in preventing, controlling, mitigation effects of fire and life safety. Develop the engineering methods and techniques related to fire and life safety. So that's your building design, that's your starting to get into your active systems and all of your passive systems. Analyzing and evaluating the technical solutions of life safety problems, putting those into effect into a set of drawings that can be actioned upon by a contractor to get installed. Interdisciplinary role of assisting project team and design team. The reality is life safety, fire protection engineering, as I tried to point out earlier, it's not just those red boxes and red pipe. And then pretty much every discipline across the board when it comes to design of a facility, design of any type of function, there is a active fire protection role in it. You know, the civil engineer is managing laying out of fire hydrants. The architect is laying out the compartmentation and the separation. The mechanical engineer has to make sure their penetrations through those fire barriers are protected. Each of those items, we can go down electrical engineering, all of them. Fire protection engineering touches them all, and the active coordination of all those things becomes the role that a fire protection engineer plays within a project. So IBC, IFC, kind of the standard building codes that we have here in the state, provide as well as the industry standards such as NFPA and various other forms, FM Global and whatnot. All these represent our code requirements. So these are prescriptive, and then the language that allows us to do any type of performance-based design, where we're looking at equivalency and looking at modeling and creating systems that meet or exceed the model code compliant systems. So here you go, Rick.
All right. One of the biggest questions that I've have received over the years is related to fire protection. Is as mentioned previously, prior to 2013, the state didn't even recognize fire protection engineers and allowed mechanical and electrical engineers to provide those services. But as you look at the history of the codes, especially with the fire codes, prior to the 60s and even into the 60s and maybe early 70s, fire protection systems and listed components were very limited. National recognized testing laboratory requirements were not that extensive back then. They are very time consuming and costly to maintain. So there wasn't a lot of options out there within the components of a fire alarm system or a fire suppression system. Generally, back then, buildings and structures, interior finishes were relatively simple. Most of the time was wood, metal, concrete. We didn't have the composites, we didn't have the plastics that you see in today's built environment. So pre-60s and even further, It was pretty straightforward. We understood the fire hazards of the building components of the built environment. We had very limited components available to select from to provide the protection that was required. Basically, back then, you would do a sprinkler system off a pipe schedule. You knew through the pipe schedule you could put this many sprinkler heads on this size of a pipe. So it was relatively straightforward and simple. But as the built environment progressed, the industry started becoming more involved. They recognized additional hazards were being introduced into the built environment through the plastics and composite materials that we're seeing today, like these tables, the desk. Back in the 60s, this would have been wood. So along with the more complex building materials, as they became more available, the industry started increasing the options available for providing the protection. They understood the hazards a lot better, so they were able to provide a lot more variety on ways to protect the built environment hazards. Along with that, as you saw in the previous slide with the refinery, the chemical processing industry also had to make changes to adapt to the built environment demands, which increased the hazards within chemical processing plants. And you still see that today. There's a lot of fires in chemical processing plants still. Due to the fire incidents and investigations during that transitional period, again, the fire protection industry has provided a lot more options. Along with that complexity, they have it's increased the demand for fire protection engineers to understand the fire dynamics, the fire science behind the hazards that are present within the built environment, and adequately protect the asset and the public from those hazards. In addition to that, the code compliance also started recognizing performance-based solutions. So when performance-based structural fire protection engineering is designed and applied properly, the structural integrity of the building should be maintained during an exposure to fire or thermal radiation, which it does impact the means of egress, which Eliot will cover later. The listing requirements within the national recognized testing laboratories, like I said, have gotten very extensive. They include all the materials. It's pretty much like a recipe. You need to follow the instructions as the UL listing prescribes in order for you to ensure that the system will provide the protection that you're expecting. Continual compliance changes and challenges are introduced regularly. Everybody realizes halons, they used to work really good. Now they're banned. Same thing's occurring right now with a lot of the foam concentrates. They've introduced some additional fire protection features. They now have aerosol fire suppression, which has recently came on the market and obtained its listing. They've got gels now that are recently coming out. Some of these gels are pretty interesting. You could submerge your hand in some of the gel and hold a mat torch to your hand and it won't burn it. So they're continually bringing new products to the market. It's a very dynamic industry. As the complexity of the built environment and the buildings and furnishings increase, there's definitely a demand for more specialized roles to understand the hazards associated with the hazards and the built environment that we're exposed to on a daily basis.
So, with that kind of as your background, we can start looking at what it is that we're using for protection. So we got the active protection, kind of as this goes over, you're talking about things that are in motion, things that are, you got your water systems, you've got your alarm, your active items and components placed into the building in order to either detect or react to a fire scenario. So the simplistic list, you got fire water supplies required for facilities, fire and gas detection systems within the building, so your alarm component, your fire suppression system. So as Rick was going over, it's not just water, although water is the baseline and the go-to on that when available. But you've got the other types of systems that can be used and placed within the building to do suppression. Smoke control and management systems. So this really relates to mostly specialized systems, but when you have an atrium, you got something that's serving more than one story. When you have a high-rise building, that's going to start kicking in various extra components. And a high-rise just defined as having a floor level above 75 feet. So, we're talking 7-8-story buildings. We're not going that high to start kicking in these extra requirements. Building operating system networking, so your auxiliary functions within that. We also have our passive systems, which I already kind of touched on a little bit earlier, but passive being always there and basically always functioning. So these are the items that are built within your building, as simple as just the compartmentation, such as the room we're sitting in. Physically, with the doors closed, this fire is going to remain within the space if it starts here. The intent being you're not going to allow it to break out in the hallway where people are trying to egress. So we got the 4 main areas of this. We got the structural fire protection system. So this is actually, your ratings upon your structural columns, your beams, those things that allow your structure to remain standing so that you can get the egress out of the space. You got your compartmentation, as I'm talking about, within each individual space. The idea that you want to maintain a compartment that a fire will not break out of, so that you are maintaining your egress path for those that need to get out of harm's way. Your opening protection. So opening protection being that any of your elements that are passing through these compartmentalized items, in particular firewalls, smoke walls, of that nature, we want to make sure that everything that is penetrating those walls is still maintaining that rating. The idea of saying, you've got a 2-hour constructed wall that separates 2 different spaces. Well, when you just punch a duct through there, when you punch some conduit through there, you want to make sure that it still is a 2-hour wall after that action is done. So then you get into your fire stopping and material systems, specifically, your conduit penetrations, various things like that. You're running through that wall, we're going to maintain that separation. So a lot of these end up being required to be tested and approved nationally. You got so your nationally recognized testing laboratories, UL, FM. Those are the items we're going to specify. And I think most every discipline when doing construction is going to specify something that is UL listed. You're going to rely upon the fact that there has been a third-party test that has gone in and proved that these things function as promised. So we kind of can look at those fire stop situations as being something specific for UL. So what we get to, and kind of at the heart of what we're doing for this protection and the protection of the occupants is looking at the egress analysis. And so what we have is the available safe egress time. So the available safe egress time, that is pretty much what your fire is. Your fire is going to start, and this is the amount of time that is actually available for the occupants. So from the time the fire starts until it actually creates an untenable condition, a condition where someone cannot survive within your egress path, that's your time weighted. So that's where your compartmentation keeps things out of that corridor, allows people to exit. That's where your suppression system slows down the growth of the fire to the point where you have a time for people to egress out. Now, what we're going to compare this to is our required safe egress time. So required safe egress time is physically how long does it take for someone to react to a fire alarm, react to a situation, and actually exit the premises. So this is getting into that actual time from the start of the emergency until they have exited out. And what we're shooting for is that you want your available safe egress time to be in upwards of 1.5 times your required safe egress time. You want your buffer, you want your safety factor built in there. When looking at this, there's things that we have to take into account in this. It depends on the type of system. It depends on what it is that you're actually type of use. So you get your time to detection. So in an automatic detection system, that's just the time it takes for your detector to react to the fire. That could be a few minutes. A detector can be smoke detector, heat detector. It can be your sprinkler system is technically a heat detector. However, if you don't actually have an active alarm or water suppression system in place, that time to detection is someone's nose. So how long is it going to take for someone to actually physically react to and smell smoke? Human nose is actually very sensitive, and a lot of times they can actually beat the smoke detector, provided that someone's located within the vicinity of the fire. So your time of warning is, the actual time that your alarm system's going to go off. You got your time to react, which surprisingly, you'd all think that, as I said earlier in this, that we're all going to react like we're in third grade and we got our fire alarm and it's going to go off. But the reality is a lot of studies have been done, and you've got minutes. Many minutes, and it depends on the population of the facility you're looking at. If you have school-age children, they may react quickly or they may not. You've got preschool-age children, they're not going to react very quickly at all. You can go all the way up to hospitals, nursing homes. Your reaction time there is going to be very extended because it's no longer going to be the person reacting, it's going to be the staff reacting to those situations. So this is a pretty big variable. One would think, okay, alarm, we're all just going to pick our stuff up and leave. That's not the case with every population, and it's not the case with every building type. And then you get into your timer response. So this is going to be, I've heard the warning, I've reacted to the warning. Now what am I going to do? Am I going to pick up my computer? Am I going to finish that email? Am I going to make sure that I've turned my computer off? Who knows? So there's a bunch of decisions that are being made by the occupants during that time. And then you got your time of travel, which one would think, okay, that's going to be your longest time. But once you start adding all these other components up, your time of travel is probably very lessened. And what we really want is to actually have a time with a margin. So our safety factor, we want that extended enough so that we can cover those populations and allow people to react. So this is kind of covering all the parts and pieces of that fire protection, all those components. So that compartmentation, the suppression system, the alarm system, all of these are to either shorten some of these early components or lengthen the time for these later components. So what we do with this is to get into the assessment of the hazard. The first thing that we're going to do in a brand new project is we're going to actually look at our fire risk hazard. We're going to assess what it is that actually is a hazard. Do you have just a standard office building with standard components? Are you actually putting some more hazardous material? Is there a process going on? Are you storing hazardous materials, explosives, flammable and combustible liquids, all those things? We're gonna go through and we're gonna kind of play detective on those items and determine what it is that the actual fire risk is for the space. And then we're gonna go choose our adventures, what I kind of look at for the code study, and figure out what path are we gonna follow and how are we gonna provide protections for what it is that we've decided, or the owner has decided is gonna go into this facility. So the fire hazard assessment accomplishes the three objectives here, provides an understanding of the hazards, enables a specification of fire protection equipment, and forms a part of the overall risk assessment of the facility. We have to determine what is the risk before we can determine what it is we're going to apply for those solutions. So they have a broad applicability for fire risk issues. It can be used as a tool for looking at what is important to that facility, as far as like safety and in particular occupant safety. And with taking that fire risk assessment with other factors, you can get a risk-informed decision making. And there's various complexities to this. Like I said, your standard office building, maybe not so complex, and you're going to understand what those components are. Most everyone is. But sometimes you're going to get into situations where the owner may not necessarily understand what it is they're asking for and what it is their risks that they're actually putting into these spaces. And so it becomes that conversation piece. So it's important to consider all stakeholders, as I was getting into there. The reality is, the people that actually have an opinion upon these hazard assessments. You got the regulators. So you're going into code officials are going to have an opinion about how it is that you manage a facility. Your facility owners and operators, which can be the same people or it can be two different people, and that can be a very important distinction. The employees within there, the people utilizing the space, which may not necessarily be the operators or the facility owners. You can look at your emergency responders. What components did we leave in there that allows the first responders to come in and deal with a fire scenario? The insurers, the neighbors, the communities, the investors, the design and construction team, the engineering team. All these people have some type of input into this. So depending on complexity of project, this can be a simple meeting and could only involve a few people, or it could actually have to involve all of these people if we're trying to do something unique, if we're trying to in particular, if early on it's established that we're not going to quite follow the code, we're going to come up with a solution that matches those project needs. And then you got tenants. So.
All right, getting kind of down there. Next topic we're going to kind of briefly talk about is emergency response principles. What does everybody do if you hear a fire alarm go off in the building? Everybody evacuates and leaves the building, correct? It's not necessarily true. The emergency responders actually enter the building while everybody else is running out. So it's very important to ensure that the fire protection features that are provided to ensure safe evacuation of the occupants are also there, they're robust and in place for the emergency response team to have available when they're running towards the fire hazard that everybody else is running away from. An emergency has specific characteristics that are dependent upon local facts and factors. The building construction type, the type of fire protection that is provided within that facility, etc. The essential basic tenets of emergency response, particularly in an emergency setting, are to address specific needs involving the location, the facility, building occupants, and rely upon the fire protection systems and features provided. As fire protection engineers, it's important to understand the principles of emergency response, their actions, and make every effort to ensure that the fire protection systems are reliable, they're robust, because we want to make sure that the emergency responders that show up at a fire event are able to go home at the end of the day to their families. Now we'll get into a little bit about performance-based design. We've touched on performance-based a little bit as we've progressed through this. What is performance-based fire safety design? It is a method to demonstrate how fire science can be used to solve fire protection problems in the built environments, especially when, as Eliot mentioned, when you're into complex facilities. Industrial settings are another example where fire hazard assessments are a key component, because a lot of the building codes, the IBC and the IFC, they don't really necessarily address the industrial process safety hazards. That's where you have to get in and understand the hazards that are going to be present, because each industrial process facility has their unique little differences. We use it to gain a better understanding of how a building will perform during the event of a fire. We use fire modeling for a lot of that to assist us to understand the dynamics of the fire with the materials that are going to be present in order for us to properly protect the asset and the occupants from that potential hazard. The objectives of a performance-based approach: we want to identify the key attributes of the performance-based design, review the advantages and disadvantages of using a performance-based design over prescriptive-based solutions. And we want to provide a series of steps offering a framework or process for the performance-based design approach, which kind of summarizes in the discussion about performance-based. The last topic we're going to cover today is wildfire safety. That was a request for the presentation. We all realized that there was a lot of wildfires last year. We had several in Alaska. There was quite a number of them in the lower 48. So what is important about wildfire safety, especially with homeowners? It's very important to make sure that you talk to your homeowner's insurance where you live, especially if you're in an area where there's wildfire-prone areas. Home insurance companies have tools to help you understand what hazards might be present and how you should implement protective measures to mitigate those hazards. Insurance companies use their own proprietary underwriting and rating requirements, which is why it's important to contact the home insurance company, your home insurance company, if you're in a wildfire interface area. Why homes are at risk to wildfires. A lot of times they're built adjacent to a fuel source, trees, forests, vegetation. There's lack of standardized building, fire, and planning codes, typically. There's misconceptions on how a home will ignite during a wildfire. Overgrown vegetation, which is typically persistent during droughts. So the objectives of trying to help protect your home from a fire is identify the key attributes. When does a wildfire disaster occur? That was a mix-up on the slides. Most often, they occur as a result of worst-case conditions, severe weather, topography, fuels. The conditions allow a wildfire to spread rapidly, building intensive heat. As wildfires spread towards the communities, homes become an additional fuel source and become simultaneous ignition sources to other homes, so you get that cascading effect. I think that occurred quite a bit in California last summer. As additional fires spread, fire protection resources are quickly overwhelmed because they're getting pulled in all sorts of different directions, resulting in a reduction of firefighting effectiveness because they're focusing their attention on protecting the homes rather than trying to combat the wildfire. So individuals living in wildfire urban interface areas are not only responsible for reducing the risk on their own property, they also have an important role to play in their community preparedness. Prevention involves individual efforts to diminish potential fuel sources near homes by removing vegetation, providing fire breaks between vegetation and homes, use of ignition-resistant construction materials, metal siding is a good example of that, and understanding wildfire behaviors. Understanding the wildfire behaviors is similar to the fire triangle. We have weather is a contributing factor, temperature, humidity, precipitation, wind are all factors that influence the weather, contributing factor. During hot and dry weather, plants dry out very quickly and ignite easier. Wind increases the supply of oxygen to a fire and causes preheating of fuels in front of the fire, which in turn dries the vegetation in front of it and creates a higher hazard. Topography is the second element of the wildfire behavior triangle. How is that important? Steep slopes carry fuel or fire uphill at an increased rate. Canyons can act as channels for wind to funnel. Slope orientation is another contributing factor. Though we can't change topography, understanding its influence on wildfire spread is important. And then, of course, fuel sources. Potential fuel sources in a wildfire includes living and dead vegetation, homes and its coverings, and any outbuilding and structures that might be adjacent to that. Fine fuels such as grasses and needles ignite easily and burn quickly, carrying the spread of the fire. That's why it's fairly important to keep your lawn watered and mowed. Ladder fuels are like shrubs and small trees. And then you have the heavy fuels such as trees, which create crown fires. Structural ignition sources are the crown fires, extreme type of wildfire burning in the tops and the crowns of trees that produce embers that travel at great distances. We have surface fires, which are small flames burning through grasses and ground debris, such as fallen leaves, down trees. Embers, it's a principal factor in continuing fire spread within a community. They are burning pieces of airborne wood and or vegetation that can travel very long distances and ignite additional fuel sources. So how do we mitigate wildfire risk. We need to thin our trees and shrubs. We need to prune our lower branches on any of our vegetation around our homes. Remove highly flammable plants and vegetation. We need to create fire breaks with walking paths or driveways. Yes, and by doing that, homes can survive a wildfire. It's not where the home is located necessarily, it's how ignitable the home is and its surroundings that's important. Home ignitions are determined by the condition of the home and its immediate surroundings. And there's additional information specifically in Anchorage on this website that you can look if you're interested in further information within Anchorage. Okay, I think we're on to the conclusion. So as we've covered, fire protection has evolved over the years and it now requires specialized engineering discipline such as fire protection engineering. Fire protection industry has evolved with an increase in available equipment options for design of fire protection systems. It's also involved because of the evolution of the built environment and the increasing complexity of the materials being used within the built environment. We have options. We can look at prescriptive-based designs, but we need to recognize that they're rapidly being replaced with performance-based design solutions. In fact, this spring, the state's going to be adopting the 2018 IBCs, and along with the 2018 edition of IBC and IFC, there's a big change in recognizing and explaining how to provide a performance-based design as an equivalency to the prescriptive requirements that are pretty prevalent in the 2012 codes. Most states and other countries are increasingly recognizing the need to establish fire protection engineering as a separate specialized engineering discipline. Again, the state of Alaska has adopted that in 2013. So, in conclusion, especially on complex projects, get fire protection engineers involved early to help step through the fire hazards that might be present and work with the owners and the AHJs to come up with alternative solutions as a performance-based option. Any questions? I haven't personally seen where, oh. Okay, the question was related to the evolution of the fire suppression agents that are available on the market. For example, halon was very, very prevalent back in the days. It's now banned. The foam solutions for AFFF's foam suppression systems are now being recognized as an environmental hazard, so they're rapidly becoming banned. And then what applications have we seen with using the aerosols and the gels and the other new technology within suppression? Did I capture your question right? In Alaska, I haven't seen aerosols or the gels being applied on projects. I'm not sure if other states have been looking at them or not. One of the things that I always thought that the aerosols would be good for are smaller electrical equipment spaces. I always thought that they would be an attractive solution for like wind turbines, because an aerosol suppression system is probably not much bigger than that camera up there, and you probably hang 4 of them in the corner of this building with a thermal link to it, and it would provide the protection for this space. And then once they go off, You just, all that's required is to disconnect the expired canister, put a new canister in there, and hook it up, and you're backing up in operation. So it's very little downtime, very easy replacement. I think that they haven't been around very long. It's kind of a recent trend.
Is there an issue with occupant interaction? I mean, if they release with people in the room, is there an issue with
When they initially came out, there was a concern with the aerosols because they generated some heat when they were being expelled. But the industry manufacturers have recognized that as a potential hazard, and over the years they have revised their component to mitigate that hazard so that it is not as much of a hazard today as it was when the aerosols first came out, because they're putting cooling cells within the aerosol canister to cool the propellant before it enters the room. No, aerosol is basically almost a little canister that's mounted on a bracket that you can. Oh. What's your question? The question was is the aerosols similar to a water mist system, right? And that's a completely different technology. It's proprietary. I think it's a lot of sodium, potassium. Yeah, is a lot of what they use in those aerosols, but a lot of it's proprietary within the manufacture of the suppression. Sir.
Yes, I was curious about the synthetic building materials, and are those regulated based on flammability or the hazard from smoke inhalation, or how is that evaluated? And it sort of makes me recall that, like, there was a building, a high-rise in London, I think, that had like a plastic or synthetic facade that when it caught fire, it was just like a big chunk of plastic burning. I mean, it seemed very hazardous.
So the question is, how are the regulatory agencies addressing the plastics on facades of buildings due to the hazards and the fire incidents that have occurred over the years with building facades? Actually, that's one of the things that the building codes have really started focusing their attention on. The listing agencies are starting to do a lot more extensive testing to implement additional requirements for the manufacture and installation of these plastic facades, because there have been a lot of fires that have escalated very dramatically and caused some loss of lives because of the building facade catching on fire and the fire traveling up it. So it is recognized as a concern. The industry is taking strides to impose requirements and implement some testing methods to ensure that the flame doesn't spread, the smoke doesn't develop in excess.
So pretty much most building materials, but facades, ceiling materials, wall coverings, various things like that do have code required flame and smoke spread ratings. So those are actually we have to stay within limits. So the materials that are put into the building for floor coverings, walls, there's a list of these items. They all have to actually pass UL type tests where they are, or ASTM tests, where they are exposed to a fire, and then they have to stay within the limitations of flame and smoke spread on those. So those all kind of exist. So in the instance of one of those London fires, I believe, that was something where I think that material was actually tested. But some of what you have to have perspective on, in particular those tests, is those tests are all standardized, right? So they're meant to represent a given fire scenario, whether you're putting it into a tunnel with a fire going across or something along those lines. When you change the orientation or you change, kind of how it is that the material gets applied in the field versus how it was tested. Sometimes you end up with situations where an unforeseen circumstance comes up, where you get a flame spread that in a material that was tested and actually passed, that doesn't necessarily meet that same performance when in an install condition. So these are things that are aware of. And I think when you look at any of our building codes, our fire codes, all these things are related to specific fire incidences or disasters that have happened. Something happens, someone comes in and evaluates what it is, what were those conditions that created that scenario, and now we get a new building code section or a new requirement or a revision to a requirement. So I think these things are kind of that evolving type, and one of those where flame and smoke spread, especially the testing and related to building facades, is something that's kind of ongoing and developing at this point. So, yes.
At what point do you get involved in the design and engineering of our structure? And how do you interact with the designers of that?
Okay, so the question is, at what point does the fire protection engineer get involved in the design of a structure? The reality is that varies. Ideally, depending upon type of structure, I'd like to be involved in the concept phase. I'd like to be having that conversation, kind of as we went over earlier in the presentation. When you actually have those stakeholders having that early conversation about what it is the facility is, what are we putting in it, and how it's going to be utilized, where it's going to interact, where it's going to be placed even. All these things have to be kind of brought in. The reality is, fire protection engineer can be hired from that concept phase all the way through to looking at after the fact. I mean, I think Rick has a quote that he really likes to put out, and I'm stealing his thunder by taking it. But fire protection engineer, we'd like to be involved early. FPE, we'd rather not have that actually stand for what is it? Fix the problem at the end. And sometimes I think we get drug into that situation and that scenario a little more often than we'd like. So. So the question is, with the banning of halon, did we lose a very effective product? And I would say yes. I would say the reason that it got installed everywhere is it worked very well. The reality is we can look at a lot of products. We can look at asbestos. Why did it get put everywhere? Because it worked very well and it wasn't very expensive. So the halon systems, I think the uniqueness to the halon was the pressures that it operated at. And so the piping system and the design you could do was a lot more efficient at the time to utilize halon, and than it was to look at other suppressants, and therefore their actual solution required to implement.
There wasn't a lot of options back then either.
True, as Rick's stating, there wasn't a lot of options. Certainly things like the banning of halon actually drives the innovation to create something new. But they're never a one-for-one drop-in replacement. And that's where, we'd all love to come in and say, okay, here's an exact equivalent for the system so that a building owner can just swap it out, keep their piping, whatever else. But the reality is, no, their physical operation is different, and therefore we got to replace all the components, and that's unfortunate. And the reality is, halon's banned for future use. So anyone that has a halon system currently, I believe right now it's perfectly legitimate to leave it in place. If it doesn't go off, you're doing great. If it goes off, now you've got to replace it because you're not going to be able to get a refill on that tank. So, any other questions? Yes.
Similar to computer or digital age, it seems like fire systems that have been responsible for go out of date quickly and are no longer supported and get renovated. And what's your experience as far as longevity of electrical detection and alarming systems?
So let's rephrase the question or try to capture it here. So opinions on the longevity of fire alarm systems as it relates to components going obsolete and no longer being supported and being able to be updated and remodeled. I think that's the nature of these components. I don't know that the technology is always going to be driven forward, and what it's going to be driven by is that a manufacturer has to go out and get these products listed They will go get their UL listing for these so that they can be installed within these facilities, and they will maintain that product for a certain period of time for to actually manufacture, sell, and support. But eventually, due to changes just in technology, codes, and other things, they're going to have to be driven to another product. And I think that's inevitable because you're going to have either changes in technology where we've gone from traditional like analog type systems where you just have circuit boards within them or relays to the point where a lot of stuff that's getting installed now is addressable, as in it is a computer. And you're using addressable and communications systems within there where it's a computer running it. And so that has kind of been a transition. And so I think that obsolescence component probably will remain as a piece of kind of the industry. And it's unfortunate that, a facility that lasts 20 years and just depends on when that panel was spec'd that went in, right? Was it at the end of its service life at that point? And then you get stuck with a situation where during that service life, you're having trouble replacing components or doing your remodels. I think that's just the nature of the industry. Rick, you probably have a little more experience. I don't know if you have something to add to it.
No, you summarized it very well. When I first started in this industry in the fire alarms, it was all relay-based control logic. So depending on complexity of your system, you'd have several panels full of relays in order to perform what you can do now on a computer. And as Eliot said, technology is going to drive it. I think on the typical average, from what I've seen, fire alarm system life expectancy is about 20-25 years on the average. So, for building owners, it might be something to consider, in their plan for the facility, about a 20-25 year cycle to look into whether or not they have to upgrade their fire alarm system, but chances are that they probably would. Suppression systems are a lot better as far as that goes, especially if they don't get activated, except for once a year when you test them. A sprinkler system, 50 years or more. There's sprinkler systems that have been in place for 75 to 100 years in various locations. So. The question was, is the recent fire in Kaktovik where the school burnt down. I haven't heard much about that. What I did hear was it was 35 below zero. Pipes were frozen. They were in trying to thaw the piping system out, and it ran away from them and caught the building on fire. I would imagine it probably was. I don't know what they had in there, but typically that would be what I would predict. Do you know what they put in schools?
In schools?
Wet or?
It's wet in schools.
Yeah.
However, whether Kaktovik had it, I don't know.
Yeah. Any other questions?
Power transmission lines as a vulnerability or hazard here in Alaska. I know there are a lot of incidents in California, like PG&E shut down all the transmission lines. Here we also have some experience with Kenai River hydropower. Could those transmission lines be a really potential hazard with vulnerability?
There's a spark. There's a potential hazard there. Yeah.
Is there anything that we could do, like fuel management or shaded maybe fire breaks and things like that to stop it?
So the question's about power transmission lines in relation to what happened in California kind of over this summer and fall, where the transmission lines were causing sparks to come off and ignite wildfires. When looking at that, I mean, obviously that's going to fall to the utility to manage their equipment there when it comes to the development of that spark, right? That's a matter of how that got installed, how that reacts to the winds, which is actually probably causing those cables to come into proximity enough that you had that arcing and you had those sparks. The management of how to not get that to spread, that would be looking at creating that break. And so that's looking at managing that fuel source and fuel load that is available for that spark to ignite. So, when we look kind of that fire tetrahedron that we kind of began this with, you need your oxidizer, you need your fuel source, and you need your heat, and then you have to have it to turn into, the conditions have to be right to turn into an uncontrolled reaction. So you have to look at breaking something there. And in this instance, probably you'd have to looking at breaking that heat source, so the heat source being the spark, and you'd have to look at breaking the fuel source, which would be, that biomass that was around those spaces. So is there an easy solution? Yeah, cut everything down within around it. But, that's not cheap. So, you got to look at how you work that, how that works out. So.
Can you manage the biomass to kind of stop fire from spreading? Like, can we optimally do that?
So the question is, can we optimally manage? Can we optimally manage the biomass to generate off the biomass? The reality is yes, but of course, biomass systems being something of a different topic, but you have to have enough to burn. I participated in biomass heating projects throughout this state. You have to have something to burn, whether you're using chips or whether you're using cordwood or anything like that. These things are it's not the small stuff that you're probably chopping down around the power lines and you're probably maintaining year after year. You have to let it grow enough to be able to burn. So if you let it do that, then now you're talking about creating that fuel source off of those sparks off of the transmission lines. So it's a trade-off.
And as an offshoot on the energy sector, there's a big growing trend globally right now on energy storage systems to store alternative energy power that's developed, like winds, solar. There's been a lot of fires that have occurred in these energy storage facilities, and kind of summarizing this whole discussion of the evolution of codes and the technology advancements, the industry demand for these battery energy storage systems has increased so dramatically over the past several years. There's facilities that are looking at putting gigawatt hours worth of storage in these facilities. So there's been a lot of fires that have occurred in these battery energy storage systems. They had one that happened in Arizona just last year, injured 8 fire responders. One of them critically. He didn't die. He was in critical condition. 3 of them got severe burns. But the demand for these systems has increased so dramatically that the fire codes and the like UL have not been able to keep up with the demand. So I think last year in South Korea there was 26 of these facilities that caught on fire. As a result, here in the last 6 months, NFPA has published a whole new standard. First edition ever been released is 2020 on fire protection for energy storage systems. So when you look at the IFC, as Eliot mentioned, IFC will tell you when fire protection is required. When it's required, then you will now go to this new NFPA standard that has just been published. I think it was released in November of last year, on how to protect that facility from the fire hazards. So it's a constantly evolving industry, and the technologies and the manufacturers are continually evolving and bringing out new products on a very continual basis. Any other questions?
If there's no question, let us thank you.
Thank you.